Alright, so this is my smart plant care system. I'm hoping to eventually scale it up for real, like large-scale agriculture. I have some ideas. So this is just like a demonstration minimal viable product. There are plenty of people out there who have made like smart watering systems, but they're usually pretty simple. They just detect whether the soil moisture is high enough or not for the plant, and then water it when it needs to be. My system is a bit more involved. So this right here is a lithium polymer 3.7 volt battery. This is an I2C hub to communicate with sensors. I'm not actually using it right now, but I was thinking I might have to, which is why it's still plugged in. This right here is a MOSFET switch. It is a digital switch. Basically, it controls the pump, which is back there. So this is very accurate and it can turn on and off quickly because it's digital. So it actually, you control the speed using pulse width modulation. So full speed is 255, the integer. This right here, if you can see, is the Shao ESP32 S3 microcontroller. Whoops. And then connected to it right here is the Wi-Fi antenna. So we're not using this I2C hub, but I am using this I2C hub. There's 6 ports to connect many of the sensors and communicate with the microcontroller. This right here is the AS7341. It's a 10-channel light sensor. 8 of the channels are specific wavelengths that are blue light, green light, and red light. And then one of the channels, the 9th channel, is near infrared, and the 10th channel is clear, which it's very accurate, and basically the clear channel can be used to detect the intensity of like ambient light. So I'm using that because plants, when they're in different growth stages, need different wavelengths of light. Ultimately, I'm hoping that to adjust it. So right now it will detect those wavelengths and tell the user which ones, how much of each it's getting, and that's meant to help the person who's growing the plant to know like how much, if it's getting the right light at the right stage. So eventually we'd want to incorporate some grow light LEDs because those you can control red, blue, and green wavelengths. This right here is a soil moisture sensor. It's a DF robot capacitive soil moisture sensor. It's what detects the soil moisture. It's not perfectly accurate. These are used for hobbyists, but they're relatively cheap. I hope and plan to get a more expensive one that's more accurate and uses FDR, which is radio waves basically in the soil, and it's not as affected by soil density and salinity. This right here is a rotary encoder. It's basically a knob you can turn and push in to select things. And then back here, this is the SH35 temperature and humidity sensor. It's extremely accurate. It's pretty much industrial, commercial grade, or pretty close to it. Hopefully you can see that. And then back here is the OLED display screen. It stands for organic LED. And then the RTC, which is a real-time clock. So if the Wi-Fi doesn't pick up the date and time, it can fall back to the real-time clock to get the correct time. And then this right here is the submersible pump, which actually sends the water to the plant. And then of course there's a bit of a water bottle there for me to demonstrate this. So real quickly, I'm just going to come over here and show. So this is a deep stake. It goes in the plant and it actually allows the water to go down to the roots of the plant easier. That's what that guy is. And then this is just a stake holder to hold the tubing. So yeah, I'm going to go ahead and demonstrate it. Alright, so here is the organic LED display. It's showing the temperature currently and humidity as well as the date and time. If you depress the encoder, so I had a little bit of challenges with the encoder. It doesn't work perfectly yet, but I'm working on it. So if you depress it, you have to kind of hold it down. We'll go to the menu. The font is a little bit small, but then we can select So whoops, plant profile. And right now, this is data that it is getting currently, but I need to format it better. It's not looking quite right. Okay, then we turn it, go to light levels. So this would show where the light levels are. I didn't have, so I forgot to mention, I ordered a bigger screen, a larger display that's full color, to be able to have this menu be the correct size and displayed correctly, as well as to show the light level wavelengths as a bar graph. However, Amazon, there was a bunch of issues, basically, to put it simply, and half the order came, but it wasn't any of the stuff I ordered for this, the screens or anything. So I placed a second order for overnight shipping with DigiKey, and those parts also did not come on time. So I did not put that as a risk in my project. I didn't realize normally when I order parts a week in advance, they come just fine. But this time I was not able to get the screens and stuff here. So right now, this is just mock data. It's just all placeholder until I get the bigger screen and can actually display this more accurately. Okay, so I push down. So now if I go to the pump, let's see if you can see back there. So I'm going to turn it on. Okay, and I turned it off. I'm going to set that down, and I will show you real quickly. You can see that it definitely did water the plant. So for now, I'm still working on getting that calibration correct with the soil moisture sensor. There's a little bit more work to do to, like the calibration, it will calibrate and it has the correct range, but I still need to finish making it so that it will water the plant when it needs to at the right time. So there's still a bit to do on this, but that was just a demonstration that it works. When the bigger screen comes, I'll be able to actually make the menu really work instead of just having each of those sub-menu items have like mock data basically in there. So anyway, that's the demonstration. We'll go back down, or sorry, I'll go show on the screen on my computer the code and explain, and be able to show you a little bit more of the data from this. All right, so real quickly, I just wanted to finish the demo. I know it's a little bit long, but just want to make sure to really show what's going on. So you can see right here in the serial monitor the different wavelengths of that 10 channel light sensor. So 415, 445, those are wavelengths for blue light. 515, 555 is green, yellow. 590, 630, 680, that starts to get to the red. And then of course clear, white light, and NIR is near infrared. It is updating quickly because I had to make the polling pretty quick. And then down here, plant 0 represents the plant profile. So if you have multiple plants, but in this case we just have one sort of mocked up. Raw represents the actual raw data, or signal number that's coming from the soil moisture sensor, and moisture is 0%. So right now it's literally just out in the open air, which is why showing moisture as 0%, which is dry, and raw is up close to 700, which means the dry plant. So I'm going to shine a blue light real quick on the 10 channel sensor. And you can start to see those numbers go up in the 445 and 480 range. Of course, some pass over to green. And that's blue light. Here's red light. You can see the 630, 680 start to increase in that range. And this is green light. you can start to see that. So anyway, eventually, oh, whoops, and if we go to white, this is what happens with white light. Okay, yeah, so 535 is the max number for the intensity. And then real quickly, so that soil moisture sensor is completely in open air and dry, which is why it says 0% moisture. The raw is 700-ish. Here I'm going to stick it in water now. And you can see that the raw data number goes to the 300s, and the moisture goes to 98, 99, 90%, 100%. It's not perfect, but it's pretty close. Alright, and so what I did was, I previously had created this smart plant care system on my own using Arduino and this microcontroller. I didn't have the rotary encoder connected, and I had the soil moisture sensor unconnected as well for a brief period, but didn't have the rotary encoder, and the 10-channel light sensor was separate. You could read the light by independently in the code. It wasn't attached to connected to the microcontroller. So that previous code was following the format that or it should have been. Yeah, I believe so. Okay, so that code followed basically the Arduino format. I don't know if you can see here, where basically for the Arduino, for the microcontroller, you have a void setup and a void loop, where you basically set up your program and the sensors and everything, initialize them, and then the loop basically just runs indefinitely for however long the microcontroller's on. And so it's just a big bunch of code, all basically in one place. For this project, so I reformatted everything so that the code is actually object oriented, and it's more modular, and it's easier to upscale with multiple sensors and pumps and multiple plants and things. So that was the goal of this, and so let's move on. That was long. All right, so I'm going to try to go through this the best I can pretty quickly, so we don't take too long. But anyway, so with Arduino or microcontrollers, it works a little bit different, but I had reformatted it for the object-oriented format. So, like I said, there's a setup and a void loop. There's not usually a main. It's all just a bunch of code on one page. But because I have different objects that I created, so I'm able to import these like custom libraries I created with the class, and so we initialize the stuff that we have. So our display, which is an OLED display, the light sensor, temperature, humidity sensor, the system time, and the display manager. And then these are the labels for the serial monitor for the wavelengths. And specifically in this case, we just set up plant 1, but the user should be able, like eventually this will have multiple plants, and I'm calling them watering zones so that it can scale again. So we set up, we use enumerate, and I use app state here to set this up because this display was really small. I mentioned previously that I had issues ordering the parts. I ordered them over a week ago, and Amazon and DigiKey had challenges delivering them. I won't go into all the details. So in order to compensate for that, I had to do a few things, and I'll explain here, that like mocking the data and stuff of what it would be, because I learned that in our testing class. So anyway, so we create these states. Basically, we don't change the display or run the function until the user is selecting that state so that it updates correctly. And also, we don't use too much memory or cause issues that way. Alright, so I added the encoder. I had to get the specific addresses for the encoder and register and the button. It does click, so that's how you select things. and then I created this basic menu. It will be updated once I get the bigger screen and once I have a little more time to make it a little bit better. Here's our void setup. So basically the beginning part that runs. So we have a serial begin. We need that to happen. We delay 2 milliseconds. Basically, we wait a little bit. Then our wire begin. These are the pins for the SDA and SCL, which is a serial data clock and the serial, serial clock and serial data. And so when we use I2C to communicate, it's a special protocol. Basically, we need to use the specific pins on the microcontroller. We set the clock frequency at 100,000 hertz. We're going to begin for the display, the OLED. We begin our system time, and our sensors are initialized, and then also we begin the spectral sensor, which is the light wavelengths. So by using object-oriented programming and refactoring my code, it makes it a bit cleaner and also, like I said, easier to scale. So then the void loop, we want to make sure that we update all our sensors immediately when the loop starts every time, so we're getting the correct updated data. And then I have this here just for debugging to see the serial output for the wavelengths and the plant moisture. Just makes it easier to verify that the data is accurate and correct, that it's working correctly, both here in the code and on the microcontroller, because I can compare and see what they look like. Then I added the rotary encoder. We need to be able to detect the button depress. So, excuse me, this rotary encoder, so we're going to select our item again from the menu, our state. This allows us to select to turn the pump on or off. And again, this will get updated more, so it's a little bit better, but I just wanted to show the basic implementation. So we wanted to be able to read when the encoder is turned, the knob is scrolled, and it has 16 bits that it works with 16 bits. So you have to bit shift and send two separate bytes of 8-bit to make it work, and so that it reads correctly. So that's what's happening here, so that when you actually click the button, it registers. And I need to look at it a little bit because it does take a little, like you have to kind of hold the button down, whereas I thought you should just be able to click it one time, but need to look at responsiveness, but I didn't have time. Then we need to render our logic for displaying which menu we're displaying on the screen from the state. And again, this is where, like I said, I had to mock up stuff, because normally this would show a bar graph of different colors of the light wavelengths, but because I didn't get the larger display, I just marked it with light levels and then some static text. Same thing with the settings. This is, I wasn't able to fully implement this, so the user needs to be able to enter their Wi-Fi SSID and the password so that they can connect to the Wi-Fi. They need to be able to rename the plant, because plant 1 is default, or in this case plant 0 actually, but anyways, this needs to be like plant 1, plant 2, plant 3. That way you can have multiple sensors and multiple pumps for multiple plants. And then also calibration for the soil moisture sensor. So it's static for now and marked up, but I'm planning to change that. It is polling pretty quickly, or updating quickly. So again, I'm still looking into the what's it called? How quickly it responsiveness, basically. Yeah. So okay. All right. These are our header files. So for each of the classes. So this is for the system time. Let's see. Where did I do? Yeah. Okay. So we have to import the libraries, the correct libraries for the real-time clock. NTP is the network time protocol, I think. This uses the internet to get the time and date information, and then of course the libraries for the Wi-Fi and UDP. Yeah, real-time clock, UDP time client. So this is, the header is basically like our blueprint. So we're telling it what we're needing, and the different variables. Here's the display manager header. So again, we have to import the library for the OLED display, and then our enumerator for the screen. The screen that we're using, it's the OLED SSD 1315 for now until it gets replaced. Private, I'm using private for the variables. We don't want to change some things, so they're private and encapsulated. And this is to keep everything consistent and working correctly for the display and the functionality. Obviously, some things are going to want to be updated or accessed, so they're public. In this case, yeah, we can see those variables: rendering home, rendering light, rendering watering, and the menu. So that's the header for display manager. Watering zone header. So one thing here is that I've set this up so that we want the user so the goal is to hopefully create this as a real product eventually, but anyway, preferences is so that the actual data can be stored on the microcontroller. So like if the user calibrates the sensor, if the power turned off the microcontroller or the battery died or something, we don't want them to lose the calibration settings for each thing. Like, it would be annoying. So I've set it up so that it gets that correct amount. And then so these are all integers. The uint is 8 bits, I believe. The uint 1632 in this case. We're using 8. So preferences again is our memory to store stuff that we don't really want to be accessed, stuff that we do want to be accessed. The pulse width modulation, so we're using a MOSFET controller, which is 0 to 255. I explained already. 255 is the full speed, and so this allows us to control how much water the pump can send. Once I've still got to get this implemented and calibrated, but I was just demoing what we have. So anyway, okay. So the system time logic. So those were our blueprints, the header of the class, and then this is the .cpp is like the implementation of the logic for that specific thing. So our system time, again, for the sake of time, I think this video is very long, so I'm going to just kind of go through. Again, a lot of the time in date stuff, I was able to just use the logic from the previous code that I'd written. It just wrapped it so it was object-oriented. I feel like this is mostly self-explanatory. Sync with the NTP, make sure the time is formatted, get the formatted date. So I'm just going to go through this pretty quickly, actually, without spending too much time on it. Again, so our functions, we're making sure that we're using it, calling it on the class that we created. So display manager class, render home. We want to display the temperature, humidity, date, time, like you saw. Again, I used a lot of the code that I had and just wrapped it so it was object-oriented. In this case, again, it's mocking, so this will get updated, so it'll display the real data, but that's mocking. This is real data that does get shown, and then clear the buffer. We want to clear the screen and update things. Watering zone, I'll go through quickly. I hope this video is not too long. Basically, the manufacturer for this particular soil moisture sensor on their website gave different numbers for what's dry and 100% water. I had to go adjust these so that they accurately represent the actual 0 to 100%. And my values are slightly off from what their values would be, but that's because the code they had was for the Arduino Uno. So again, I had to change the 10-bit resolution, I had to adjust it so that it works with the ESP32 S3, which uses, I think, 12-bit resolution, if I remember correctly, instead of 10-bit. So that adjustment had to be made. And then map invert, so we wanted to make sure that the high number, 700, is 0%. When it's dry, it's 0%, and 330, the low is 100%. And then the PWM, yeah, so that is the code. I hope this video is not too long. I did also use something called PlatformIO, which is how you make it work with Arduino instead of using the Arduino IDE. But anyway, that's the code, and yeah, there's more to come. So I'm hoping in my next iteration to, I'm planning or hoping, unless something changes, to use the cloud database to update and create the plant profiles for users, and then also to be able to capture the data for the soil moisture sensor and the light stuff so that it can go into the cloud database, and then eventually have a mobile app where the user can see a display of the over time of when things have been watered and soil moisture at different times and light levels. So yeah,